So if our query point falls in this bin here, meaning it gets scored as 0, 1, 0, so maybe our query point is right here. And so according to the lines that we threw down, it would have a binary vector 0, 1, 0. And then what we do is just go and look within this box and look at the distances to data points 4, data point 8, and data point 11. The question is, do we know we're going to find the nearest neighbor? And so hopefully this shouldn't be such a trick question at this point or such a challenging question. The answer is no. We know that we're just thinking about returning an approximate nearest neighbor because the nearest neighbor could very well be in some other bin and have been split from the bin that our query point was put into. But the important thing here is that the situation is even worse than what we mentioned before when we just threw down one line, because the chance of splitting our query point and its nearest neighbor is even higher when we're throwing down multiple lines, because there's more of a chance that one of these lines or multiple of these lines will split our query point from its nearest neighbor. So what we see is that when we think about throwing down multiple lines, what we're trading off is accuracy for speed, because there's a greater chance that searching within a single bin, we're not going to find our true nearest neighbor, but we can search much more efficiently. But there's actually even better news, which is we have some control over this approximation that we're making, and we have control over how much computation that we are going to perform our nearest neighbor search. Because in particular, we don't have to just search the one bin that our query point falls into. We can also search nearby bins. So what does it mean to be a nearby bin? Well, let's look at this. Okay, so remember our query point was, let's say, somewhere around here. The bin that it falls into is 0, 1, 0. So what are the nearby bins? They're bins 0, 0, 0 and 1, 1, 0. And what we see, which makes sense if you think about how these vectors were actually defined, is that the nearby bins are the ones that are just one bit off from our current bin indices. So for example, going from a 1, flipping that bit to a 0, we get to the orange bin. Or if we take our 0, flip it to a 1, we get to this blue bin. So it's just changing the score of the point by saying that it just fell on the other side of the line that defines the current bin. Okay, so what we can do in practice, if we go back to our hash table, is instead of just searching bin 2, you can't see that at all with this color. Let me switch colors. Instead of just searching bin 2, we're going to look at the binary encoding of 2, and then we're going to go flip bits and search these nearby bins. So then we're going to search bin 0 and bin 6 in this case. Okay, so we're going to compute not just distances to these points here, but we're also going to compute distances to these other data points. And we're going to hope that if our nearest neighbor didn't fall into this pink bin here, maybe it was in the orange or maybe it was in the blue. And so what that assumption is saying is that we're assuming if our nearest neighbor fell in one of these other orange or blue bins, is that relative to our query point, there was only one line that split the nearest neighbor from the query point. But there might have been two lines that split our query point and its nearest neighbor. So if that were the case, so let's just draw a little picture over here, and let's say this is our query point, and this here is its nearest neighbor. Well, it could be that we threw down two lines that split these 2 points, and in this case, we'd have to search 2 bits off. So we'd have to search, now flipping 2 bits, taking our 0 turning it into a 1, and taking our other 0 and also turning it into a 1 to search bin 7, and then also consider the distances to all of these data points here. And again, if we found a nearest neighbor that was in this bin 7, what that would mean is that we had exactly this case where 2 lines separated our query point from the nearest neighbor. So just to make sure it's very clear, the quality of the nearest neighbor that we return can only improve as we search more and more neighboring bins. So what can we do in practice? Well, typically when we go and use locality-sensitive hashing to perform nearest neighbor search, we think about running the algorithm, searching nearby bins, flipping bits, more and more bits, and searching all of those bins until we've run out of our computational budget that we've set for that search. Or alternatively, maybe you have a standard for how good the nearest neighbor should be from the query point. So, as long as the point we find is within some epsilon distance of the query point, we're going to say that's good enough. So then in that case, you would just keep searching until you found that neighbor within that epsilon ball of the query point, even if you hadn't run out of your computational budget so far. So the cool thing here, relative to the approach of just throwing down one line, is we can actually control this approximation versus the complexity of search trade-off that we're making, because we can get better and better approximations the more bins we search, but we can cut off that process at some point if we've searched too many points. We've run out of time in performing this search. Whereas if we just threw down one line, we wouldn't know where to stop the search. We wouldn't know which set of points were closer or further. So that's part of the benefit of throwing down multiple lines. Okay, so just to recap what we've seen so far about locality-sensitive hashing, well, the way that we partition our data points is we throw down some h different lines, and then we're going to score every data point under every line and use that to create this binary bit vector. And then we're going to take that and we're going to use that to encode a bin index, or really that's going to serve as the key in forming a hash table that lists all the data points that have that specific binary vector or bin number. And so this data structure is going to serve as basically the direct analog of what we did for KD trees. So this is going to be a fixed partitioning of our data points into different bins. And then when we go to perform our nearest neighbor search, when we have a given query, we're going to use this data structure that we've created, which is just simply a hash table, and we're going to search bins and nearby bins to return our nearest neighbor, a really approximate nearest neighbor. And so we're going to use this same hash table for every query we have. So although there's a cost to forming this hash table, which we'll discuss a little bit later, we can reuse it again and again and again every time we're doing a query for a nearest neighbor.